All right, I'm sorry for the late start, though I'm guessing you don't care that much because less time is less new material, right? That basically, yeah. Congratulations on being here today. All right, I just wanted to say a bit about the schedule for the coming days. This is an adjustment for what's in the syllabus. Today and Monday, we're going to be talking about the first two sections of spectroscopy in the textbook. These are not numbered chapters. I don't know why the text made the decision. There's three sections that sort of divide 351 and 352. They are spectroscopy sections A, B, and C. We'll be talking about A and B together today and next time. And then for 4 classes after that, we'll talk about spectroscopy C. And then the final few classes, we'll talk about some chemistry that happens later on in the text, but is traditionally covered in 351, so we'll continue to do that too. That is chemistry with radicals, which are molecules with unpaired electrons. So it's sort of different from everything else we've done in 351, which is why we're sort of tacking it on at the end. What we'll be doing in these spectroscopy sections is sort of teaching you how to be scientists. That is, how do you prove that the reactions that we've talked about worked? How do you demonstrate the identity of a molecule? In some ways, this is a topic out of analytical chemistry. Most of you will not take any analytical chemistry classes as part of your majors or your preparation for MCAT or DAT. Nevertheless, analysis of data is an important part of all science, and in particular, medical science. So even though you may not necessarily going to be in your future analyzing data to prove that a molecule has a specific identity, you might be analyzing data to demonstrate that a patient has a specific disease. And so the ability to look critically and analyze data and think about what it's telling you and what it's not telling you is a pretty important skill, which is why we're teaching it to you. All right. So with that in mind, prepare yourself. I know it's new material. I know you don't care about it today, but on Monday you will care about it. So do your Monday self a favor and make room for it in your head. All right. So the first thing we're going to talk about is a technique called mass spectrometry. And mass spectrometry is a way of, how do you even spell it? Mass spectrometry. There's a Y at the end. All right, close enough. Mass spectrometry is a way of measuring, sort of, the molecular weight of a molecule. So this is tremendously useful if you have a molecule and you think you've made it and you think it has a certain identity, you know its molecular formula, you need to confirm that that's actually what you made. What's presented in the text is a very basic picture of mass spectrometry. The field has exploded and is used in all kinds of science now and is much more sophisticated than what we'll have the time to tell you. But mass spectrometry is based on the idea that charged particles move in characteristic ways in magnetic fields. So most of the organic molecules we've dealt with, molecule M, are neutral. And mass spectrometry deals with charged molecules. So you have to have a way of ionizing the molecule and making it charged. So the way that's presented in your text is basically you can ionize a molecule by bombarding it with a beam of electrons. You don't need to worry about how you generate the beam of electrons. There's a filament that electrical current passes through that emit electrons in a beam. You can direct that beam of electrons at a stream of your molecules. This is sounding like Ghostbusters at this point. And the electrons that hit the molecule will actually eject an electron from the molecule, sort of by electron-electron repulsion. So this process generates a version of your molecule that has has one fewer electron than it used to have. And we call that molecule the radical cation. It's the radical cation because we're basically assuming most molecules that we can isolate have an even number of electrons. And so if you lose one electron, you now have an odd number of electrons, and one of the electrons is unpaired. It's a cation because you used to have the same number of electrons as you had protons in your nuclei, and the molecule was neutral. Now you've lost one electron, so overall you're positively charged. Okay? The fact that this molecule, having been bombarded with electrons, is now a radical cation has important consequences for the kind of mass spec data that you're going to be seeing in this chapter. All of this is prelude, though, because the radical cation now has a charge. And the idea here is that charged particles move in characteristic ways within a magnetic field. So you take this, in the mass spectrometer, you take the radical cations that are generated at this stage, and you send them on a journey down a detector tube. You do this by accelerating them through a slit in positively charged plates, so negatively charged plates. So the radical cation is attracted in this direction toward the plates. Most of the particles hit the plates, some of them go through the slits. This is all done in the gas phase in vacuum, so the particles are just floating freely in a vacuum. And then the particles encounter a magnet, and the magnet deflects the charged particle. This is physics, and that's all I'm going to say about it, but you remember how magnetic field can change the path of a charged particle. There's some kind of right-handed rule, and good luck figuring out which one that is. And so the path of the charged particle changes in the magnetic field based on two things, based on the mass of the charged particle and the charge, which is going to be called Z. And the thing that the mass spec experiment measures is the ratio between M and Z, the M over Z ratio. That's the mass to charge ratio. So a particle that has two charges is going to be deflected differently from a particle that has one charge. A particle that's twice as massive is going to be deflected differently from a particle that's half as massive, all right? Fortunately for us, the thing that we care about in this experiment, we've ionized our particle. Our particles all have one charge, Z equals 1. So if Z equals 1, the M over Z ratio that this mass spec experiment's going to measure, it's just going to give us the mass. So these are the data that you get. At the end of the tube, there's a detector. And the detector essentially scans through all of the M over Z ratios and counts the number of ions it sees at each M over Z ratio. And from this, you can learn some things about your desired molecule. So, for example, here I show you some data for the mass spectrum of methane. Now, methane, CH4, the mass of the radical cation would be CH4, and then we'll just put a dot and a plus. We don't know which of those 4 bonds in methane lost an electron. We just know that overall, so this is the Lewis structure of methane, we just know that overall one of them is down an electron. Keep that in your brain somewhere because that means that one of those bonds is weaker than the others, and that's going to be important later on. But the mass of methane you can calculate, we're talking about in terms of molecular weight, we're talking about 12 for carbon and 1 for each hydrogen, so we expect 16. And if the charge is 1, we expect an m/z ratio of 16. That's for the peak, that is this radical cation of methane. We call this the molecular ion, which we also abbreviate as M, like that, because that's our molecule that has just been ionized and its charge is equal to 1. Now, if you look at the data for methane, what you see, you sort of have to count and interpolate, but this largest peak is at an m/z ratio of 16, okay? However, we also see a peak at an m/z ratio of 17, and we need to talk about why that is. So you may have learned that about 1.1% of carbons are C13. So that means 1 out of every 100 carbons has an extra neutron in it. So you would expect 1 out of every 100 methane molecules to weigh not 16, but 17, because C13 weighs 13 instead of 12, right? And indeed, that's what you see. The y-axis in a mass spec is how many times the detector sensed that ion. So if 1 out of every 100 methane molecules has C13 instead of C12, then 1 out of every 100 observations should have an m/z of 17 instead of 16. Yeah?
Sorry, can you explain one more time where we got this percentage from?
That's just known. If you look at, let's see, is the number on there? Yeah. If you look at the atomic mass of carbon, it's 12.011. But carbon-12 with only 6 neutrons and 6 protons should have a mass of 12. So what's the 0.011? The answer is, as you learned in general chemistry, that atomic mass is a weighted average of all the isotopes of carbon that are naturally existing. And so people can measure this. And whereas you've got sort of like 98.9% of carbons have 6 protons and 6 neutrons, and that isotope is carbon-12. The natural abundance on Earth anyway of carbon-13 is about 1%. Yeah, and you can actually look this up on Wikipedia if you want to spend a couple of hours just dinking around. You got hours to kill, I'm sure. Maybe while you're eating your cereal, just Google isotopes of hydrogen. You'll see all the natural isotopes of hydrogen, or isotopes of nitrogen. It turns out that carbon is the most abundant. There are a lot of other isotopes of relevant organic molecules that have sort of 1 extra neutron, though by far carbon is the most abundant. Also on this list that could contribute to this peak that's larger than we expect would be deuterium. So that's hydrogen. We've talked about deuterium before. Sometimes I abbreviate that with a D. Only 0.01% of hydrogens are deuterium. So that means that this peak at 17 for methane mostly comes from carbon-13. But I could list some of the other isotopes that are relevant for organic molecules. 0.4% of nitrogens are N15 rather than N14. And 0.04% of oxygens are, oh shoot, I need like, when you turn 45, you're going to start like not being able to see small things anymore. So looking at the small print. All right. Good. So this peak that shows up, as I said, at 16 is the peak for the molecular ion. The peak at 17 is the M, we call it the M+1 peak, but that's the peak that has either a C13 or a deuterium or an N15 or an O17. All of those individual possibilities could contribute to the M+1 peak. Of course, in the case of methane, the only two things we have are carbon and hydrogen. And by far, the biggest contributor to that M+1 peak is carbon. Now, as your molecule gets bigger, you're going to start to see other peaks at higher mass units, because the more atoms you have in a molecule, the more ways there are to have +1 neutron. And so for the kinds of molecules we see in my lab, actually there are a number of peaks, M+1, 2, 3, 4, 5, and so on, just because when you start to have hundreds of atoms in your structure, there start to be many more ways to have +1 neutron than there are to have no extra neutrons. All right. A couple of, just as a preview, sometimes we see in some organic molecules, we see quite a large M+2 peak. This mostly comes because of the fact that for chlorines, 24% of chlorines are C, shoot, am I going to get that wrong? C37 instead of C35. CL37 instead of CL35. It's about 76% of chlorines would be C35. So if you have a molecule with chlorine, you're going to see two peaks. One is the base peak, or the M molecular ion peak, that corresponds to the 76% of chlorines that have C35, and the other is going to be 2 mass units higher than that, representing the other 24% that have CL37. Bromine is also interesting in that way. Bromine and chlorine are weird because, again, the natural abundance is about half and half for bromine. So about 50.6% of bromines are bromine 79, and the other 49 point whatever percent of bromines are bromine 81. So again, for bromine, if you had a molecule with bromine in it, you would expect to see about half of your observations in that base peak, the molecular ion peak, with a mass of whatever it is, M, and then the other half at M+2. Yes?
So when we're calculating the expected value of M, is it better to go off of the mass numbers in the periodic table, or the atomic, or the number in the most abundant isotope?
Great. Yeah. When predicting what the mass, what you should observe in a mass spec experiment, should you use these weighted average isotope numbers from the periodic table, or should you use the numbers for the individual isotopes? You should use the numbers for the individual isotopes. Now, for here, at the level we're doing this, decimals are not necessary. So carbon is 12, hydrogen is 1, nitrogen is 14, and so on. Mass spec has evolved to the point where if you're going to do what's called high resolution mass spec, where decimals do matter, you do need to use the masses just for the isotopes, individual isotopes. You can look those up. It won't be important for you here. Also, even if you forget to do that for bromine or chlorine, if you see a mass spectrum for a molecule with bromine or chlorine in it, it will be obvious because you will see the presence of an M+2 peak with a characteristic ratio relative in intensity relative to the molecular ion peak. I'm just going to scroll down and give you a preview of that. Here is a molecule with, this is, I think, yes, isopropyl or 2-chloropropane. And it's telling you it predicts molecular weight of 78 and 80. That's from using carbon has a mass of 12, hydrogen has a mass of 1, and then chlorine has a mass of either 35 or 37. You expect that to be in a 74 to, no, I think it was 76 to 24, who cares? It's about 3 to 1. You expect that to be in a basically 3 to 1 ratio based on the natural abundance. And indeed, if you zoom in, you see the peak at the M peak at the expected molecular weight for Cl35, and then the M+2 peak at the expected M over Z ratio for Cl37. Okay, so if you see that characteristic 3 to 1 ratio, that's like, oh, there's a chlorine there, which can be useful, especially if you don't know what the formula of your molecule is. Yeah?
Did you explain what the fragments are?
I will. I haven't yet, but I will. Because you're noticing there's a bunch of stuff going on down here that I'm ignoring yet, and we'll talk about that. Here is the related molecule for, this is 2-bromopropane. Again, the predicted mass is based on the idea carbon is 12, hydrogen's 1, bromine is 50% 79 and 50% 81. You look at that molecular ion peak, you see the M peak at 122 and the M+2 peak at 124, and they're basically 1 to 1, or 5149. Okay? Again, that is a dead giveaway for a bromine. Even if I didn't know there was a bromine in this molecule, if I saw that pattern, an M and an M+2 peak 1 to 1, that means there's a bromine there. It could get more complicated if there's more than one bromine. People have worked all of that out. Your text doesn't have you analyze that, and neither will I. You're welcome. Yeah. Okay. So fragments, let's talk about that, because you're noticing that the spectra are a little bit busier than what I'm telling you. In general, we will focus our attention on the molecular ion. People struggle to figure out which one that is, because they will say, is it always the highest molecular weight peak? No. The M+1 peak, for methane is 17. The M peak is 16. Okay, well, is it always the next to highest peak? No, because if you've got a chlorine, the highest peak is M+2, the next to highest peak is M+1, the peak that's your molecular ion is 2 away from that. So if you're looking for hard and fast memorized rules, I got nothing for you. You're going to have to actually think about the data. Okay? So you have to know that you're looking, in terms of the molecular ion, you're generally looking for the tallest peak in the highest cluster of peaks. Understanding that you should see a small M+1 peak representing all the C13, and that you might see an M+2 peak if you've got a chlorine or a bromine. Okay? Again, we're not in the business of memorizing rules. I'm not raising computers here. I'm raising scientists. And you've got to know how to analyze the data. All right? So let's talk about the fragments. Fragmentation of the molecular ion occurs because, and actually this makes sense based on what you've learned about structure of organic molecules, if I take an electron out of one of those bonds, suddenly that bond is half as stable as it used to be. So it makes sense that there could be some bond breaking events that happen. So let's talk about that. The other thing you need to know, by the way, is that mass spec only sees charged particles. If a particle is neutral, it doesn't show up. So let's talk about what happens to the molecular ion, the radical cation for methane, this sort of issue of fragmentation. To do this, I'm going to draw a version of methane that's kind of silly. I'm going to assume that one of these bonds only has one electron. Okay, and now the molecule's positively charged. I'm not actually going to worry about assigning formal charge to the atoms. But the idea is that this carbon and this hydrogen are both sharing that one electron. I'm not using a line between the carbon and the hydrogen because the line means 2 electrons. All right? If that bond is only half as strong as it used to be, then, and we've just hit our molecule with a beam of electrons, so our molecule is really high energy, it's actually quite easy for the hydrogen to leave as just hydrogen atom or hydrogen radical, a hydrogen with 1 electron. Notice that this hydrogen is neutral. It is not charged, and so it is going to be invisible to the mass spectrometer. What will be left after hydrogen leaves? CH3. Hydrogen left is neutral. The radical cation was positively charged to begin with, so if you subtract something neutral from something that's positively charged, it's still got to be positively charged. So you've got the CH3 cation now. This is, has a mass of m-1. If we're looking at it, the charge is 1. The m over z ratio here would be 15 instead of 16. Do we see a peak at 15? Yeah, and the intensity tells you that that happens at least almost 50% of the time. We lose a hydrogen. That kind of fragmentation is possible. Now, you've never seen that before in solution. That's totally fine. It doesn't happen in solution. It does happen in the gas phase, in the vacuum at high energy, when you've just shot a beam of electrons at your molecule. All right, questions about that? Yeah?
Is it possible for it to get hit by 2 electrons, or is that not really?
Can it get hit by 2 electrons? I don't really know. It's like, well, once it's positively charged, wouldn't the electrons be attracted to it? I don't actually know the physics. It's a good question. I will also say that there's a lot of ways of ionizing molecules. Because of this fragmentation issue, bombardment with electrons is no longer the favorite method, and especially if you want to do mass spectrometry on very large biological macromolecules, you don't want this kind of fragmentation happening at all. So there are other techniques for doing it, which we can, if you're interested, if you're interested, you should actually go talk to one of the analytical chemists in the department, but I can tell you a little bit about it. Okay, so what about those other peaks? We've got peaks at 14, 13, and 12. Those peaks come from breaking further fragmentation of the cations. So, for example, we could lose another hydrogen atom. You've learned, by the way, that carbocations, especially primary or methyl carbocations, are not that stable. And if you accept the idea that we're at a really high energy, then it would be possible to lose a single hydrogen to get to this CH2 radical cation, which would have m over z of 14. I know you're panicking, saying, how was I supposed to know that that was going on? You weren't. The data tell you that it is, right? How else are you going to explain the presence of an m over z equals 14 peak? Similarly, you could lose another hydrogen ion or another hydrogen atom to make this weird molecule. How have I've never seen that before. How was I supposed to know that that exists? Again, you weren't. The data tell you that it has to. And then, of course, we could lose another hydrogen to get to this weird positively charged carbon with 3 electrons, m over z of 12. All of that's happening in the gas phase. Were you supposed to be worrying about this all the time in solution? No, because in solution you were not shooting electrons at things in a vacuum. Yeah? Sorry, that's, I don't know, I meant M minus 4, but somehow I wrote Z, which looked like a 2, so I'm really sorry. Good golly, M minus 3. Yeah, thanks. All right, so that's the kind of fragmentation that can happen. Now, that's just in methane. You can imagine it getting much more complicated when you're dealing with multiple bonds. So here is the mass spectrum for hexane. The molecular weight of hexane is 86. So this is the base peak. This is here is the M+1 peak. Here are some fragments from losing hydrogens. Then there's a rather large fragment that's actually way more intense than the base peak. And you can figure out what this is if you look at, and here, rather than draw things, I'm going to copy something from my notes just to show you. I don't think it's really worth our time to go through this bit by bit. If you want to see it more specifically, you can take a look at the notes, which I will post. The idea here is simply that there are a lot of bonds in hexane, and I could have removed an electron from any of them, and then based on fragmentation after that, I might see different peaks in the mass spectrum. So real briefly, if I lose an electron from the bond between carbon 1 and 2 of hexane, and then I lose the CH3 radical, what's left behind is carbons 2 through 6 that's positively charged. This now has lost 15 mass units, and so that's the M over Z equals 71 peak, which you see here. Apparently that doesn't happen a huge amount. More common, apparently, if you look at the number of observations, is for me to lose an electron from the bond between carbons 2 and 3. I don't know why that is. But then if you lose the CH2CH3 radical, you're left with this carbocation that comprises carbons 3, 4, 5, and 6, which should have an M over Z of 57. Again, you can go back if you want and do the math to calculate what the numbers should be. But the idea is that we're progressively losing, depending on which electron was ejected from this molecule, we can then fragment the molecule into two pieces. One that's a radical that's mass spec invisible that we don't see, another that's positively charged that we do see. And so you could go down and for every one of the ones that I've drawn here, you can see a fragment. So here's the M over Z of 71 from loss of methyl radical. Here's an M over Z of 57 from loss of ethyl radical. And there are other fragmented peaks there as well. Okay. So it used to be that scientists would try to infer a lot about structure from these fragment peaks. And there's still going to be some questions that you can answer about that. But that's no longer the most important way of teasing out structure in organic molecules. I will say, though, that you can use some principles that you already know about carbocation stability to help you out. Here is an interesting, well, not that interesting, but here is a molecule, and let's say it gets ionized to form the radical cation. And then that radical cation fragments into pieces. And suppose I tell you that the most abundant fragment has an M over Z of 57. Some of this, sometimes fragment abundance correlates with the stability of the thing that the mass spec measures, which is the carbocation. you already know about carbocation stability. So think about the fragments you could get if you removed an electron from any one of these bonds, and tell me what the most stable carbocation I could get would be. What I'm asking is, imagine loss of an electron from any one of those carbon-carbon bonds, and then fragmenting of the resulting radical cation like this into a radical on one side and a cation on the other side. Now, if you think about that, what should be the most stable carbocation I could get from this molecule? Tertiary, right? Now quick, do math. C4H9. What's its mass? 57, yeah. The reason the most abundant peak for this molecule is 57 is because the most stable fragment you can get is this T-butyl carbocation. You get that, just to show you, you get that if we lose an electron from the bond between the quaternary carbon and the adjacent secondary carbon. This is that radical cation. It fragments into two pieces. It's best to fragment like this that gives you the T-butyl cation and then the primary radical versus the other alternative where the radical would go with the tertiary carbon and the positive charge would be on the primary carbon. So there's some sort of cute things you can do with fragmentation and mass spec. Okay, a couple of interesting, so I don't know that we have too much more to say about fragmentation. I want to point out some rules of thumb that you can get. We've already talked about halides and the M+2 peak. This just illustrates that. Here is Xanax. On exam day, it may be Xanax o'clock, but this Xanax has one chloro. If you did the mass spec for Xanax, you would see the molecular ion of 308 and the M+2 peak of 310 in a ratio of 3:1. That would tell you, even if you didn't know what the molecular formula for Xanax was, that it had a chloride. Similarly, here is alpha sniderol, and it has a bromine. Don't you just hate it that the textbook teaches you how to name molecules and then persistently refuses to use the name for complicated molecules? In any case, if you add up all the carbons, hydrogens, oxygens, and bromine, you get two possibilities. 300 for molecules with bromine 79, 302 for molecules with bromine 81. You'd expect to see those in a 1-to-1 ratio. And even if you didn't know what the formula was, you would know that it at least had a bromine. Couple of other interesting rules of thumb that you can get. This one, I don't know if it's worth memorizing, but your text points it out, so I'm gonna share it with you, then you'll know that you've heard it. It turns out that as long as you're dealing with sort of molecular weights of atoms as whole numbers, hydrogens 1, nitrogens 14, oxygens 16. In a molecule with only carbons, hydrogens, and oxygens, the mass of the molecular ion has to be even. In a molecule that has an odd number of nitrogens, the mass has to be odd. The reason it's that way is because nitrogens are bonded to a different number of hydrogens than oxygens are, right? In its neutral state, carbon can be bonded to 4 hydrogens, oxygen can be bonded to 2, but nitrogen can be bonded to 3. So if you have an odd number of nitrogens, your mass has to be odd. This is one way, if you don't know the molecular formula, that you can maybe predict if there's a nitrogen in your molecule. Here's the structure of acetaminophen, 1 nitrogen, and indeed the mass is odd. So I don't know necessarily where you would use that. It's possible that will come up for you if you take the organic lab in 353. There's some stuff in the chapter that I am prepared to talk about fragmentation patterns for common functional groups. I'll put this in the notes. I really don't think I'm going to ask you any questions about this on an exam, but I worry that some of you who go to take the MCAT or the DAT might find a question like this on it. So the information's there. I'll post it in the notes. You can find it if you want to, which I know you won't. The one thing, however, that will be useful that I want to show you is something to do with molecular weight. It's something that was covered in the material for chapter, I think 10, under the concept of degrees of unsaturation. But I wanted to talk about it here because it's a great way to, if you have a molecular formula, to be able to develop some ideas for what the structure of your molecule might be. So this is called, based on a molecular formula, calculating the degrees of unsaturation. I think this is a highly useful skill for the 353 organic lab, where sometimes you'll be given an unknown and you have to figure out what its structure. This process helps you limit the number of possibilities that you're dealing with. Some people, instead of calling this degrees of unsaturation, call this double bond equivalence. The idea here is that if I have a fully saturated hydrocarbon versus a mono unsaturated hydrocarbon, compare how their molecular formulas differ. Ethane versus the corresponding alkene, C2H4 versus C2H6. Each pi bond accounts for -2 hydrogens relative to the corresponding alkane. And actually you know this, right? Because you've learned perhaps before that the number of hydrogens in an alkane is always 2 times the number of carbons plus 2. Whereas the number of hydrogens in an alkene is, if you've got a molecule like this, is just 2 times the number of carbons. All right? In general, the molecular formula of an alkane that's fully saturated is CnH2n plus 2. It tells you there's 2 times as many hydrogens plus 2 as there are carbons. Similarly, if we were to compare propane, C3H8, to cyclopropane, C3H6, we would see that each ring in a molecule also accounts, there's a U there, you just can't see it, for -2 protons relative to the acyclic molecule. So if we look at a molecular formula and we compare the number of hydrogens we actually have relative to the number of hydrogens we would have in the corresponding acyclic alkane, we can get an idea of how many pi bonds a molecule or rings a molecule may have. Okay? So let's just demonstrate this. The way you can do this is to calculate either degrees of unsaturation or double bond equivalence. Degrees of unsaturation. You take the number of carbons in a structure, you multiply it by 2, you add 2, that's the number of hydrogens that you expect in a saturated alkane, that's acyclic. Then you subtract the number of hydrogens that you actually have, and then you divide by 2. And that will give you the number of pi bonds or rings that a molecule must have. So, as an example, C6H6. Okay, what are the degrees of unsaturation or double bond equivalents for C6H6? That's 2 times 6 plus 2 minus 6 divided by 2. So 14 minus 6 is 8, divided by 2 is 4. That means a molecule with the molecular formula of C6H6 must have either 4 pi bonds or rings. Now, it turns out there's actually only one way you can do that in a molecule that only has 6 carbons and 6 hydrogens. This is benzene. Count the degrees of unsaturation, 3 pi bonds and a ring. Okay? Now, of course, organic molecules have much more than just carbon and hydrogen. They also have oxygens and nitrogens. Nitrogens are bonded to a different number of hydrogens than carbons are, so you have to account for that in your formula. You actually have to add the number of nitrogens, if there are any. You ignore the number of oxygens, and you subtract the number of halides, where a halide is a chloro, a fluoro, a bromo, an iodo. Some of this, we can talk about why that is if you're interested. Otherwise, you might just want to memorize it. But this formula will work for calculating how many pi bonds or rings a molecule has to have, and that can limit the number of structures that you can draw and make it much easier to solve problems where you're trying to figure out what various unknowns are. Let me give you one example of that. How about C5H5N? How many double bond equivalents does that have? Two times 5 is 10, plus 2 is 12, minus 5 is 7, plus 1 is 8. Oh, it has 4. Right? So actually, this structure, there's only one way you could do it with that few number of hydrogens, and that's that molecule, which is called pyridine. In general, you won't have to do this with only the molecular formula. You're going to have more data, but this is going to be an important piece of the puzzle, because knowing that this molecule must have 1 pi bond, for example, if that were the answer, is going to help point you in the right direction and help get you what functional groups might be in a molecule based on the data that you use. Okay, that is it for mass spectrometry. Next time we will talk about infrared spectroscopy, which is all about detecting what kind of functional groups your molecule has.